So we start with the definition of the random variable, which is a real value function from the space omega to the real number line. So this is the example we are talking about, flipping a balance point. Head and tail, those are the items inside our omega, and we define the random variable, which is the function. It is going to assign values to h and t from the real number line. So xh becomes 1 and xt becomes 0. So in that way, you can count the number of heads when you perform this experiment. So if you have a discrete random variable, the range of x is countable. If it is a continuous random variable, x is going to be an interval. So the values that x can contain will be any value within this given interval, let's say a and b. Say, for example, daily temperature, heights, weight. And so likewise, you can find several variables, examples for continuous random variables. Because we can say, okay, so the today's temperature is 29.7 degrees Celsius. You can have fractions, right? You can say the height of a certain player is 152.3 centimeters. The weight is 110.3 kilograms. Likewise, you can give decimals, fractions, right? So those are continuous type of random variables. And you are familiar with this notation. We'll use that also because we'll need them when we do Poisson processes and so on, right? The terminology and the notation that we use, when it comes to discrete case, we use the term probability mass function. I hope you are familiar with this, probability mass function, or PMF. Right? So that is how the distribution of a discrete random variable is defined. Right? So when we say the distribution of a random variable, that means it will show all possible outcomes of that random variable and the probability of their occurrence. Right? So if you can express all possible outcomes of a random variable along with their probability of occurrence, we call it the probability distribution, right? So when it comes to discrete case, we call it a probability mass function. And when it comes to continuous case, we call it the probability density function, or PDF, right? And then the cumulative density function, it is common for both. What is the notation we use for cumulative density function? We use CDF, right? CDF, the notation is capital F. This is how we write it. You find the CDF by adding all the probabilities for x up to whatever the x you want here, right? So whatever the x you have, where you want to calculate the probability, right? So summing up that, you will get the CDF. In the same manner, when it comes to continuous case, you have to integrate fx from the lower bound up to whatever this x you want, right? Should be x. Capital X less than simple x, right? So the summation is for the discrete case and integration is for the continuous case. So when you calculate probabilities, there are also you use the summation and the integration for discrete and the continuous cases respectively. How do you find the expected value? If it is a discrete case, you sum up x times px, right? For x in x. And for the continuous case, you integrate x times fx dx. And it is from whatever the support of x. Right? Support means where your function is defined. Right? So over the support from the lower bound to the upper bound, when you integrate x times fx, where fx is the PDF, Px is the PMF. Right, you can get the expected value. Right. So how do you calculate probabilities? So by looking at the distribution function, you can calculate probabilities by summing up over the range you want. When it comes to continuous case, you have the PDF, it will be a function. And then you calculate the area under the curve for the given interval. So that will be your probability. So this function is the PDF. Right? So if you want to find the probability in between A and B, what do? You integrate the PDF from A to B. So that will give you the probability, right? So the probability for continuous case is the area under the curve. For the discrete case, you have to look at the values and add them together, right? So can you give me some examples for common discrete type of probability distributions? Discrete type of probability distributions. I'll give you one. Bernoulli distribution is discrete type. What are the other distributions you have learned under discrete case? Poisson distribution. What else? Binomial is there. Binomial distribution. What else? We'll be using Poisson distribution a lot in stochastic processes, right? What are the other distributions? Geometric. Negative binomial. You can't forget the uniform distribution, right? Okay, so you usually write alongside with their parameters. Say, for example, for the Poisson distribution, you have one parameter. So you say X follows Poisson. Parameter is lambda, the red parameter. For binomial, there are two parameters. No, sorry. You say X follows binomial, two parameters, the number of trials and probability of success. So likewise, we usually write them like this. What about some examples for continuous distributions? Okay, we have the uniform distribution, the continuous uniform distribution. What else? What is the most common one or the widely used one that we like the most? Yes, what is the one that we use most of the time? Normal distribution. Yes, we have the normal distribution. What else? T, student T distribution, F, gamma, beta, exponential, pi square. There are many, right? So I'm sure you are familiar with this distribution. So the normal distribution, there are two parameters. We write it as X follows normal with mu and the variance. Exponential has only one parameter, say theta, right? Chi-square has on the degrees of freedom and likewise. So you can mention these distributions like that. So if you are talking about a discrete one, let me quickly do a small exercise. So I'm going to define a random variable x, that is the number of heads if a coin is tossed 3 times. Our random variable x is the number of heads if a coin is tossed 3 times. If I want to develop the PMF of this random variable x, can you find it? How do you write the PMF? You can list down all possible values that x can get alongside with their corresponding probability, right? It will be easy if you write down the sample space of this random experiment. And then from that, you can figure out what are the possible number of heads you can get if you are going to toss a coin 3 times. Can you try it? What are the possible x's? Let's write down the sample space, then you can easily find it. You may get all heads, plus 2 head, next tail. You can get TTH, THT, HTT, TTT. Right? So those are the possible outcomes. There should be 8 by 2 to the power 3, right? 2 possible outcomes. We are doing it 3 times, so there should be 8 outcomes. So those are the all possible ways that you can get the combinations of heads and tails if you toss a coin 3 times. Now, can you fill this probability, the PMF? What are the possible values of x? What is x? Number of heads. You may have 3, you may have 2, or you may have 1, or you may have 0. So possible values of x will be, there can be no heads at all, 1 head, 2 heads, maximum 3 heads. There's no way that you can go for 4 heads. What are the probabilities? There are 8 outcomes. Out of them, how many observations are there? How many events are there where there are no heads? Among these 8 outcomes, how many outcomes are there with no heads at all? There's only one, right? TTT. So the probability is 1 out of 8. Likewise, can you fill the rest? What is the value for 1? Only 1 head. How many are there? Okay, I got the full answer from Niranjana. It's only Niranjana who's Dinusha is answering. So I would like to see all of your answers. Tarushi, yeah, you are correct. Niranjana, you are correct. Yes, Ishini, yes, that's 3 over 8, correct. 2 also, it will be 2 heads is this one, again 3 over 8. All heads 1, 1 over 8. So this is our probability mass function for this random experiment. Okay. Now, is this a valid PMF? Is this a valid PMF? Or you may say, is it a legitimate PMF? You have to check 2 conditions. Can you remember? If it is a valid PMF or a PDF, there should be 2 conditions satisfied. The first one, all the probabilities that you have here in this second column, all these probabilities should be within 0 and 1 because they are probabilities, right? You cannot have negative values probability. You cannot have values more than 1. So all the values you see under the column PX, they should be within the range 0 to 1. And the other condition is when you add up these px values, they should add up to 1. This is the total probability. And if it is a probability distribution, this total probability 1, that is the maximum you can go for. And the probability distribution will show you how this total probability 1 is distributed among all possible outcomes, right? So when you add 1 over 8, 3 over 8, 3 over 8, 1 over 8, you get 8 over 8, which is 1. So this is a correct probability mass function, right? So if you look at this setup, you can clearly see the definition of a PMF-E1. The probability mass function displays how this total probability 1 is distributed among all possible outcomes of this random variable x. Okay. Now, can you find the expected value of this distribution? What is the expected value? You know the definition, sum of x times px. Right? So we'll do it one by one. When x is 0, probability is 1 over 8. Add them. Summation. So you add 1 by 1. When x is 1, its corresponding probability is 3 over 8. Then you have x equals 2. Corresponding probability is again 3 over 8. Finally, x is 3 times 1 over 8. So if you do this x times px and add them together, you will get the expected value. Can you find the answer? You can share the answer when you find it. It will be 12 over 8. Or if you simplify it, it will be 1.5. Okay, yeah, so you got it. Okay, tell me what is the probability that x, what is the probability that x equals 2? Yes, what is the probability that x equals 2? When x equals 2, it is 3 over 8. Okay. Okay, tell me what is the probability that P is in between 1 and 3. Let's say 3, like this. What is this probability? X is in between 1 and 3, 1 included, but not 3. So what are those probabilities? X can be 1 plus, x can be 2. There's no equal sign for 3, so that's all. 1 is 3 over 8, 2 is 3 over 8. So you get 6 over 8, right? Yeah, 6 over 8. Thanks for the answer. So that's the answer. And finally, can you find the variance of x? How do you find the variance of x? You can use the computational formula, which is variance is expected value of x square minus expected value of x. This is the mean, whole thing square. This is the computational formula. You already have ex, which is 1.5. So find ex square, that is the expected value of x square. So that will be 0 square times 1 over 8 plus 1 square times 3 over 8 plus 2 square times 3 over 8 plus 3 square times 1 over 8. That will be, this is 0, so I'm not going to write it. 4 times 3, 9. this. You will get 24 over 8, which is 3. So use it here. Ex square is 3 minus Ex is 1.5, all things square. Yes. So what is the variance? Find the variance. So the variance will be 0.75, right? I hope you all can get it, right? And there should be something that you have to double check if after you calculate variance, where variance is always a positive number. If you get a negative value for variance, that means you have done some mistakes in your calculation somewhere, right? Variance should be always positive because it is a squared term, right? Should be always positive. So if you get a negative value for the variance, that means somewhere in the middle in your calculation, you have made a mistake. So you have to double check your answer, right? So if variance is 0.75, what is the standard deviation? You get the positive square root of 0.75 and you can find it, okay? Right, so that is if you have a discrete type of random variable. Now, when you think about these common common discrete type of distributions, the Poisson binomial, and these distributions, usually we have the distribution tables, right? For the given parameters, we can find distribution tables, and without doing calculation, you can read the table and get the probability. And I'm sure you know how to read the Poisson table and binomial table. So sometimes we may use Poisson tables in our stochastic processes, okay? Right. Now let's quickly finish continuous case also. So you can move on to the stochastic processes. Okay. Let me give you a okay, suppose this is my PDF for random variable X. The support is X from 0 to 2. 0 otherwise. So this is how you write usually a PDF. There's a constant K, Kx divided by 8. Support is from 0 to 2. Lower bound 0 and upper bound 2. So again, if this is a correct PDF, what should happen? When you integrate this function over the support from lower bound to the upper bound, the integration, the value should be 1. That is the total probability, right? So keeping that in mind, can you find K, the value of K, such that this given PDF fx is a valid PDF? Can you find it? So when you write the PDF, this subscript is capital X, and within the parentheses, we have simple x, right? So this is lowercase x. So quickly do this calculation and tell me what is the value of K. So I'll start it for you. What you have to do is integrate this function K times X over 8 dx from lower bound to upper bound. When you integrate it, it should be 1. So solve this one and find the value of K. The value of k, it's 4, I think, right? Is it 4? Let's see. K and 8 are constants. Let's take it out. X dx. So when you integrate x, the antiderivative is x to the 2 over 2. Evaluate from 0 to 2. So you get k over 16 x squared. Evaluate from 0 to 2 should be 1. When x is 2 to the power 2 is 4. When x is 0, it is 0. So you get 4 times k over 16. So this will cancel out. So you get k over 4 equals 1, which means k equals 4. Right? K equals 4. So you can write your PDF as, since k is 4, it will be 4 over 8x. After simplifying, you can write it as x divided by 2. See others. Okay. So this is our PDF. What will be the CDF? How do you find the cumulative density? You integrate the PDF from the lower bound up to any x. So if you do that, you will get right. If x is x over 2, 1 over 2 is the constant, so I take it out. You get x squared over 2, the antiderivative from 0 to x. When x is square, 0. So the CDF, how do you write it? There should be a proper way to write the CDF. This is how you write it. It is 0 when x is beyond its lower limit. Within the limit, it will be x squared over 4. See, x squared over 4. That is when the values are in between 0 and 2. And it attains the total probability 1. So for all the values where x is greater than 2, CDF is 1. So if you draw the function, it will look like this. Starting from 0 up to 2. At 2, you attain the total probability 1, and it will remain there, right? So that is the CDF. If you want to find probabilities, you can do that using either CDF or the PDF, right? So for example, if I want to find the probability x less than or equal 1, you have two options to do that. One option is you integrate from 0 to 1, or you can use CDF up to 1. This is the easiest way because you have already done the integration for any x. If when x is 1, you can just evaluate the value 1 here. So the answer will be 1 over 4. If you do the integration from that also, you will get the answer 1 over 4. Right? Can you find the expected, the rth moment, EXR? When r is 1, you have the mean, the first moment about the origin. For any r value, any moment, can you find an expression for EXR? How do you do that? Integrate from 0 to 2, x to the power r fx dx. If you need mean, you do just x times fx, right? So this will be 0 to 2, x to the power r. Fx is our fx, x over 2, right? X over 2 dx. So you can write this as x to the power r, and this x, it is x r plus 1. Let's take this 2 outside. So you have x r plus 2 over r plus 2. evaluate from 0 to 2. So you have when x is 2, you have 2 to the power r plus 2, and then you have 0, right? So this is the expression for the rth moment. So if you want to find the mean, can you find it? Mean is when r is 1. Just plug the value r here, then you can find the mean. So the mean will be 4 over 3, right? Starushi, you are correct. So what you do is just plug in r equals 1. So you get 2 to the power 3, 2 over 1 plus 2, which is 3. 2 to the power 3 is 8. 2 plus 1 is 3 times 2 is 6. So you have 4 over 3. That is the mean. What is the second moment? That means you can find the variance. It's 2 over 9. Ex square is 4. So this is 2, right? So you get 2 over 9. Okay. Okay. So that's kind of a review for both discrete and continuous case. So we will be using under the continuous case the exponential distribution, and under the discrete case Poisson distribution. So most probably those are the two distributions we will be used frequently. Okay. So let me finish this review. Do you have any questions so far? Now these are nothing new for you. You have already done these things, I'm sure, in 2000 level also. So this is just a review kind of to refresh your memory about these concepts and calculations. Okay, do you have any questions from what we have covered so far? Okay, shall we move on to the next lesson then? That will be our chapter 1. So this is kind of a review. So we are moving on to our first chapter of the course. It is Introduction to Stochastic Processes. So this will be the content of the first chapter. First, we will define theoretically what is a stochastic process. And there are several classifications that you can do. So let's look at a few of these classifications. I'm writing SP for stochastic process, okay? classify stochastic processes according to following scenarios. The first one is whether this process operates in either continuous or discrete time space. And classify whether it has a continuous or discrete state space. So the time space and state space, I will explain them with the definitions when we come to defining the stochastic process. And you can have mixed type of these above two. So mainly we are looking at these three things in detail, and then all these three, let's try to find some examples of stochastic processes. Right? And as the third topic, we'll look at applications. Okay. And then we'll try to explain the meaning of Markov property. Right, so let's try to look at the Markov property. Markov chains, it's different. We do it in a separate chapter. Markov property is special characteristics that you'll see in stochastic processes, right? So, so in this chapter, we are looking at these Markov properties in the context of a stochastic process. Thermal filtration, right? Okay, so let's discuss them one by one. Okay. So let me move on to a new page. So we already discussed the definition of a random variable, right? So let me draw the graph again. Here you have the sample space omega. And you have the items inside omega. And you are going to define the function which will match or which will assign each of these items to a number in the real number line. Okay. So this is what we defined a little while ago, right? So this is the real number line. Okay, so our random variable x is a function from omega to r that we already discussed, right? And I gave you an example about flipping a coin, how to assign these values, right? So while keeping this definition in mind, let's try to figure out what is a stochastic process. What is a stochastic process, right? Now, if you think about usual probability experiments, right, random experiments, we use this term random variable to model a random phenomena at a given time point, right? So, because we are familiar with the definition of a random variable, we know how it is defined, what it does, and how to do calculations using random variables and so on, right? So we are very familiar with the random variables. So we use random variable to model any random phenomena or random experiment, you may say. At a given time, at a given time point. Or you may say, or to model a static random phenomenon. Static means at a given time point, right? At a certain time, this is the value of x. Okay, so that is what we assign using a random variable. Say, for example, if you think about exam score, right, for a certain exam given at a certain time for a certain student, there is a number. Okay, that number will not change in the next year, right? If you set for this stochastic processes exam, if you get an A, that A will be there on your transcript throughout your whole lifetime. It's not going to change, right? It's static. At a certain time point, you have assigned a value and it will remain there. Okay, so that is a static random phenomenon. But if you are going to model a random phenomenon which will change over the time, or you may say time dependent, right? So the value that you assign for a certain subject at a certain time, it is going to change over the time, right? Now, what will happen in such a situation? Now you can see the difference, right? If we are going to model a time-dependent random phenomenon. So I'll use R for random, okay? Time-dependent random phenomenon. Then what will happen? We will end up with a series of random variables, right? The same measurement measured over the time at several time points, right? So we need a collection of random variables, let's say xt. So the value of x will change with this time t, one for each time. Now we are not going to have just a single value. When the time is changing, the value of x, it's also going to change. So if there is a random phenomenon that will change over the time, the values change over the time. So that is where we are going to use a stochastic process. So a stochastic process will hold a collection of random variables, right, which will represent a time-dependent random phenomenon. Okay, so you can say stochastic process is a collection of random variables. Right? It's a collection of random variables which can be used to model time-dependent random phenomena. Okay, can you give me an example? Think about a random phenomenon where the value will change over the time. Same variable, when you measure it over the time, it will change. Okay, I'll start with an example, then you can add, right? Here's one example, number of dengue cases. Let's say in the month of October in Ampara district, let's say. So you get the numbers from MOH or somewhere. So you can record the number of dengue cases. So how will it look like? So you'll have the number of days in October up to 31. Here you have the number of dengue cases. What will happen? So there will be certain number, another one. It will go like this, maybe ribbon there, go down, right? So you can see your random variable X is the number of dengue cases. But you measure it over the time. So you'll have different values, a series or a collection of values at each time point. So on October 1st, you'll have a certain number. October 2nd, you have a certain number. October 31st, you'll have a certain number, right? So that you can model it as a stochastic process. Now thinking about that example, can anyone give me another example? Trying to think about any other example. Anybody? Population growth of Sri Lanka in, okay, yeah, that's good. So, okay, so let me explain it. Sulochana says population growth of Sri Lanka in 2022. Let me make it to a decade, right? From, let's say, 2000 to 2022. So you measure the population. So if you start from 2000 up to 2022, you can count the value, right, and draw the line, right? So that will be a stochastic process. Very good. COVID spread in percentages. COVID spread in percentage. Again, you can do it maybe monthly for several years, right? So you measure the variable, same variable over the time, right? So that is again a stochastic process. Okay. So I hope you got the idea about stochastic processes. So with that in mind, shall we write down the mathematical definition of a stochastic process? So you can say stochastic process is a collection of random variables. So this is how we write it. I'll explain the terms. Let me write it first, then I'll explain, right? A stochastic process is a collection of random variables. So that set, we write it as xt omega. And you can see omega and t. Omega is the values you see in the sample space capital omega. T will be the time unit you measured for the collection of time. So this capital T is called the index set or the time set, right? So capital T is called the index set or time set. Usually we use time set, right? And omega is called the common sample space, right? So you have a set of items that we are going to measure over the time, right? For each and every time value T, right? So that is a stochastic process. It is a collection of random variables, right? Which is defined as xt omega. So it's a function, right? Which contains the sample space omega and the time set t, right? Time set t and the sample space omega. So if you match this one as we did in the random variables, we can explain it like this. Here's our common sample space. Right? And then you have your time phase, time set, right? So let's say this is when t is t1, second time unit, third time unit, goes up to the, let's say, nth one. It can go over, right? So here's our time units. So if you think about W1, the first item, right, there will be a value measured at T1. How do you denote it? Omega, sorry, X T1 for omega 1, right? So the same notation when T is 1 for the omega 1 item, right? And then you measure the same variable when T equals T2. Then your value will be, we denote it as X T2, still for omega 1. So like this. And then suppose it goes down. So that will be X at time 3 for omega 1. Suppose in the next level, it goes up to here. Right? So this is the way you define your stochastic process. So likewise, you can draw these lines, right? For each and every omega you have in your sample space. Say, for example, if I draw the line for omega-3, suppose it goes somewhere over here, here to here, here, and goes up here. So what is this first point? X, T1 for omega-3. See, we are looking at omega-3 now. So this will be XT2 for omega-3. It goes like this, and this will be XT3 for omega-3. This will be XTN for omega-3. Right? So these are the values you see in your, this is the collection of random variables you see in your stochastic process. Right? This is our time set. This is our sample space. Okay. Right. So let me show you an example. Think about a weather station, right? Suppose you measure the average daily rainfall at 3 stations, weather stations were measured for a week, for time of a week. So if you are going to draw this setup, how can you do it? So think about it. Can you sketch this drawing to represent the 3 weather stations? You measure the average daily rainfall over a week. The time period is a week. I'll draw the sketch first. Can you try it? Then you can compare it with your answers. See whether you can get something like this. So T1 will be, let's say, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. Right? So you measure the average daily rainfall. For the first station, there will be a value. For Monday, there will be a value for Tuesday, Wednesday, and it can go like this. Maybe it's a straight line, maybe it's highly volatile, maybe they cross, we don't know. Right, so this is for XTI for S1. This will be the line for XTI for S2. Say for X3, it goes like this everywhere. Okay, so you can draw, we call them trajectories, right? You can draw a sketch like that. This is our omega, and this will be the time set. Okay, so here are a few things that you should know about stochastic processes. If you have a fixed t, for fixed t value, xt denotes a single random variable defined on omega. So what does that mean? For a fixed t, think about t4. So this should be small t. Right? For a fixed t, let's say t4. xt denotes a single random variable defined on omega. So you'll have this value, and this value, right? So it is a single random variable, that is xt4, right? xt4. So that will be for the whole omega, right? So xt4 will contain 3 values for s1, s2, and s3, right? So that is just one single variable, which will be the average daily rainfall on Thursday, right? So single random variable. If you are going to fix the other way around, if you fix for a fixed omega in your sample space, then this xt omega, right, which is the function that is going from t to r, it is the sample path. So we call it a trajectory. Correspond to the same element omega. What does that mean? If you fix, say, station 2, xt omega will be this trajectory, means this path, right? This is the sample path correspond to this omega. So omega, for this omega, you'll have how many values? 1, 2, 3, 7 values, right? You fix omega, that means you fix the station. So if you fix the station 2, it will have a sample path or the trajectory. So this is the sample path, right? That goes from T1 up to T7. So that path is for S2 only. It corresponds to the single element S2 only. It will be along the time, but for a single element, 7 rainfall measurements, right? Then if you consider the set of all possible values, that random variable xt, where t is in the time set, can take, right, all possible values that this random variable xt can take, right? So that means all possible, if you think about this example, all possible average rainfall values, right, that it can take. We call it the state space. State space of the process. And we denote it by capital S. Right. So you have two things. You have the time set T, and then you have the state space capital S. What is capital S? Set of all possible values that this random variable xt can take. Okay. Now we define two different types of stochastic processes, which is called a discrete type of stochastic process and continuous type of stochastic process that depends only on the time set of the stochastic process, that is capital T. right? If capital T is discrete, we say the stochastic process is discrete. If capital T is continuous, we say that the stochastic process is continuous, right? So that is how you categorize the two different types of stochastic processes, right? If T, what is T? The time set. If T is discrete, the stochastic process is called discrete. On the other hand, if your time set T is continuous, the stochastic process is called a continuous type stochastic process. Right. So let's look at some different examples for continuous and discrete type of stochastic processes. Now there can be different variations, right? You have two things when you define a stochastic process. You have the state space, you have the time set. Your state space can be discrete or continuous. Your time set can be discrete or continuous. So that means there can be four different types of stochastic processes. You can have discrete state stochastic process with discrete time. You can have discrete state stochastic process with continuous time. Also, you can have continuous state stochastic process with discrete time and continuous S with continuous T. Right? So there can be all mixed up models. So we'll look at the most important combinations. So the first one we are going to look at is discrete state space with discrete time set. Discrete state space and discrete time set. Okay. So I'll give you a few minutes to think about a possible scenario for a stochastic process where you have a discrete time state space and discrete time set. I'll explain one later. I'll give you an example, but first think by yourself what can be an example for this situation. Okay, so I'll give you an example, then you can think about two examples also, right? So here's an example. A surgery unit in a hospital categorize patients who undergo surgeries into 4 levels, right? So the level 1 is normal condition. Level 2 is recovering. 3, in danger. 4, severe. Right? So after the surgery, they give a certain level for their patients, whether their condition is severe, in danger, recovering, or back to normal, right? Now think about these levels. Is it continuous or discrete? You assign a certain number for patients. It can be either 1, 2, 3, or 4. You don't assign 3.4, 3.5, 2.1. There are no levels in between, right? There's no name for in between levels. So these are clearly 4 different whole numbers. So these, you can say this is discrete levels, right? So let's say the level of the patient depends on previous checkup records. Let's say checkups. Now, suppose usually after a patient undergoes a surgery, they were admitted into the ICU, right? And they monitor these patients for several hours, and then they were discharged to the normal ward, right? So usually, let's say they measure it in hourly basis. Right? They measure the patients, all the things, their respondents and all other medical, the clinical records, and they decide whether this patient is still under severe condition or whether it has been gone to in danger, and from that recovering and normal. When they are normal, they will be discharged to the normal ward, right? Sometimes these patients can go in between severe, in danger, and suddenly due to a certain complication, they can go back to the severe condition again, right? And in the recovering phase, they can go again into the severe condition. Sometimes from in danger, they will straight away heal quickly and go to the normal stage, right? That can be possible, right? So we say that the level of the patient depends on the previous checkup record. So that is possible, right? You look at what has happened in the previous hour and compare it with the current hour. Depending on the records, you can change the level. Sometimes it will change or sometimes it will stay there. It may be a patient is in danger for several hours and later it will go into the recovery or either to the severe, right? So if you are going to model this using stochastic processes, let's define XT. That will be the level of the patient at hour T, right? Tth hour. So you can write this as is a stochastic process So what is our random variable? The level or the medical level of the patient, right? It is a stochastic process with the time set t. So this is how you write it. And you can't stop from there. When you are defining a stochastic process, you have to define its state space and time space. So the state space will be let's say normal, recovering, in danger, severe. And what is the time set? So you start with the time you admit to the ICU, it's the 0th hour, first hour, second hour, third hour, and it will go 24 hours, 48 hours, and so on, right? And these checkups, let's assume that they were done in hourly basis, so there are no in-between checkups happening, right? Every 1 hour, there will be a checkup. So you can see that the state space is discrete. And the time set is also discrete. And remember the definition. we say the stochastic process is called discrete if the time state is discrete. You only look at the time space or the time set to decide whether the stochastic process is discrete or continuous. You don't worry about S. So if the time set is discrete, we say this stochastic process is a discrete one. So you look at the time set in this example. Time set, it is hours, 0th hour, 1st hour, 2nd hour, 3rd hour, and so on. So we have a discrete time set. Therefore, this is a discrete stochastic process. Discrete stochastic process. Is that clear to all of you how we decided the type of the stochastic process? You look at the time set. So according to this scenario, it is the hours, each and every hour. Hour 1, 2, 3, 4, and so on, until this person is discharged from the ICU. Okay. So therefore, this is a discrete time stochastic process. Right. So that is the first one. Discrete state space with discrete time set. Now let's look at another one, another example. If you have any questions, please stop me and ask, okay? If there's anything that you can't understand, any place where you need explanations again, please let me know, okay? The next example we are going to look at is discrete state space with continuous time set. So still your state space is discrete, but now your time, you measure it continuously, right? Can you think about a situation? So let's use the same setup for the patients, right? So these patients were in the ICU with these 4 different levels, right? So this is example 2, example 1. So you have your discrete state space, right? So S is discrete with those 4 levels. And now we are going to define our stochastic process xt. Xt is the level of the patient at time t. Level of the patient at time t. Now look at the difference between these two variables. In the first example, xt is the level of the patient at hour t. Okay, at a certain specific hour, 1st hour, 2nd hour, 3rd hour, and so on. But in the second example, xt is the level of patient at any given time t. So starting from the admitted time until that patient was discharged, right? So you are measuring the level of the patient at any given time t, right? So that time can be any value from the admitted time up to the time that the patient was discharged, okay? So how do you write it? Then our stochastic process, xt, this is how we write it, is a stochastic process with state space is 4 levels And how do you write the time set now? It can be a value starting from 0 hour up to any time value. So we'll put infinity, right? Say for now there are certain conditions. You keep a patient at the ICU up to a certain number of days, right? Usually there are restrictions like that, but for this example, we'll leave it as this. So you measure until this patient is discharged from the ICU ward. So 0 will be, let's say, from the time admitted to the ICU until the patient is transferred to normal ward. Now, in this case, what can be your T? So the hospital staff can come and look at, okay, now it's the time, now the time is 7 p.m. or 7:30 p.m. What is the state? So whatever the state that patient was from, patient was recorded at 7th hour, that will be the patient's the level, right? So hospital staff reported this patient is, let's say, in danger at 7 a.m. 7 p.m. and somebody came to the ward at 7:45 and check, okay, what is the state of this level of this patient? It is ID, right? So that is in between times you can look at what will be the level of the patient. You are not going to change it because it will be changed in hourly basis, but you can check over the time from the starting point until this patient is transferred. At any time point, you can check what will be the level of this patient. So in such a situation, it will be a discrete state space, but with a continuous time set. So in such a situation, what will be the stochastic process? You have a discrete state space, but your time set is continuous. According to the definition, it says TE, if T is continuous, the stochastic process is called continuous. So you have a continuous time set. Therefore, this is a continuous stochastic process. Can you see the difference? Is it clear to all of you? The difference between these two scenarios, example 1 and 2? Do you have any questions about this? Is everything clear to all of you? Okay, shall we move on to the next one then? So third example. So let's move on to continuous state space now. Continuous state space with discrete time set. Okay, now your S is going to be continuous, right? So here's an example. Let's use the percentage of COVID patients, right? Let's say the health ministry wants to forecast percentage of COVID patients in the country. So that will be out of the total population, how many COVID infections are there, right? So it's a percentage of COVID patients using, let's say, previous month, monthly, okay? Usually the days, right? So let's say using previous day in order to assess the spread of the disease. So in this situation, if we define xt denotes the percentage of COVID patients on a certain day. Let's say at the end of the day at 8 p.m. or so, you record that number and publish it, right? So in that situation, we have a stochastic process. So this is how we write it. Now we are familiar with this notation. Xt is a stochastic process with, you have to write the space set as the state space and the time set. With state space S what will be the value of S now? Continuous. It can be from 0% up to 100%, right? So any value in between 0 and 100. So you can have all the decimals fractions when you record a percentage, right? So it is an interval. So this is a continuous state space. So you can have any value in between 0 to 100%. And what will be the time set? You measure it daily. So first day, second day, third day, fourth day, and it will go on, right? So this is discrete. So it is a daily record, so it is discrete. So you have a continuous state space, discrete time set. Now tell me whether this is a discrete stochastic process or continuous stochastic process. It is a discrete one. Why? You only look at the time set. Now the time set is discrete, therefore this is a discrete stochastic process. Okay. Now can you modify this same scenario to get a continuous stochastic process? So you have to have a continuous state space with continuous time set. Use the same example, COVID percentage of COVID patients. How do you modify this xt, your xt? In the previous example, xt is the number of COVID patients on a certain day. If you want to make it a continuous time set, how do you define your xt? Who can try it? Look at how we did it in example 2. So similar to that, you can change the wording. Okay, so I got the answer. COVID percentage in Sri Lanka at time t. Yes, that's exactly how you are going to represent it. Thanks, Sulochana. So you got the idea. So you can explain it. You are going to record the percentage of COVID patients at time t, let's say. So that means we are going to record or update this percentage every time a patient is reported. You don't wait until the end of the day to add all the numbers. You update the percentage every time a new patient is reported. So it is happening continuously. So then it becomes a continuous time set. So how do you write it? xt such that t is in capital T is a stochastic process with state space S is 0 to 100, still it is the continuous. And how do you write the time set? Time set t will be from 0 up to infinity. Right? So we don't know when it will finish until everything should be open, right? So you start from 0 up to infinity. Now your time set is continuous, right? I think it is clear to you now. S is continuous, time set is also continuous. So you can look at the percentage of COVID patients at any time of the day over this time period. At any time of the day, you can look at the percentage because it is updating continuously whenever an inpatient is reported. But the third one, you keep the record, but you update the percentage at the end of the day, say at 8 p.m. So your percentage, new percentage for each day will be available at the end of the day. In between, the percentage will not change. So that is the discrete time set, right? Now, since you have a continuous time set, this will be a continuous stochastic process. Okay, I guess now it is clear to all of you. We described what is a stochastic process, what are the elements they should contain. The two important things are the state space S and the time set T. Depending on whether S and T are discrete or continuous, we can have 4 different scenarios. But the type of the stochastic process is only decided by looking at the time set. So if the time set is continuous, you'll have a continuous stochastic process. State space can be continuous or discrete, it doesn't matter. If the time set is discrete, you'll get a discrete stochastic process. Again, S can be either discrete or continuous, it doesn't matter. Okay, so that is how you decide or define the stochastic process, how you define S, how you define T, and then how you categorize the stochastic process into continuous or discrete. Right. Is it clear to all of you? Anything, any questions up to now? Because I'm going to stop for now. Otherwise, it will be too much. Right. So next day, I'll start with an exercise. So make sure you study these things and come, right? So you'll have to do a small exercise based on what you have done today, next week. Okay. So we'll continue chapter 1 next week also. Any questions? Is everything clear? Anything you want me to explain again? Is it fine? Okay, then shall we stop for today? I will share the review PDF file, okay, because now it's completed. But chapter 1, since we are still updating it, I will share it after I complete chapter 1. Therefore, I suggest that you keep your own notes, right? Because I'm not writing everything that I say here. So if there are anything important that you want to note down, it's better you keep your own note set. I will share this note set at the end of chapter 1, right? But until then, it's better you have your own note set with you while I'm teaching, right? I couldn't upload the video yet from the previous class. I'll do that to the YouTube and share the link with you. Okay.